Dear students, today we will start your calculus course, uh, whose title is multivariate calculus. Multivariate calculus, including functions more than one variables, and the book which is recommended for this course is already shared with you people in the prescribed WhatsApp group, and that is the James Stewart calculus. This is the 8th edition of this calculus, which is actually multivariable calculus. So let us start this book. We are going to start this book from chapter number 12, because in chapter number 12 most of the topics are covered in your previous classes. The chapter name is Vectors and the Geometry of Space. That is the title of this chapter. First of all, we'll study in this chapter the 3D space. So what is a 3D space? Just look at this figure. In this figure, you see that if this is your room in which you are sitting right now, so that is the floor of this room, from where there is a table and this thing, and if you look at your left side, that is your left wall. These are the corners of the room, this corner, that one, and that one. So that is the origin actually from which these corners are produced. So if this line, if this corner, this line is denoted by x-axis, and this corner is denoted by y-axis, and the vertical one is, say, z-axis, so this floor is made of all x's and y's. So this floor is actually called xy plane. And if you look at this left wall, this wall is made of x-axis and z-axis. So this wall, this plane is actually called zx plane, because this is made of zx. And similarly, this wall, which is actually the right wall, is made of y and z axis, so that is actually called yz plane. So there are three planes: xy plane, yz plane, and zx or xz plane, which is denoted here. You see, this is xy plane, yz plane, and xy plane. Now how could we plot a point which contains x coordinate, y coordinate, and z coordinate, is lies in the space somewhere in your room, that is in the space P, A, B, C, where A is the x coordinate and B is the y coordinate, and this vertical distance C is actually z coordinate. So this point will be somewhere in your room in the space P, A, B, C. So the point which contains three coordinates x, y, and z, that actually lies in the space, the 3D space. That is actually that ABC point. This is the ABC point. Now, as this point ABC, which is noted by P, is in the space, if you put a light on this point, so its image will be produced on this zx plane. So on zx plane there is no y, and zx plane or xz plane, y will be missing, y will be 0. And xy plane, z is missing, so z will be 0. And on yz plane, x is missing, so on yz plane x will be equal to 0. So if you put a light on this point from this side, so its image is, its reflection will be produced on zx plane, and on zx plane y will be equal to 0, this b will be equal to 0, so that is equal to 0, a is the same and c is the same. Now that point P is named as S on this plane. Similarly, if you put a light from this side, so the image of this point will be on YZ plane, and on YZ plane x will be equal to 0, so that's why this A is 0 and B and C remains the same. And now this point is denoted by R. Similarly, if you put because there are three planes, if you put a light from this side on this point, so its image will be on XY plane, and on XY plane Z will be equal to 0, so this Z, which is C actually, will be 0, and A and B will be the same. So we say that S, R and Q are the images, or we may say that reflections of this point P on ZX plane, YZ plane and XY plane respectively. Similarly, we see that along x-axis distance A has been taken. You see here distance A. So on x-axis this is distance A, and if we write A in ordered triple form, so x will be equal to A, y is 0 and z is 0, because on x-axis x will be equal to A and y and z both are 0. Similarly, on y-axis we are taking this B distance, so on y-axis x is 0, y is B and z is 0. Similarly, on z-axis x and y are 0 and z is equal to C. So this note, the points Q, R and S, the points Q, R and S are the projections of point P. These are the projections of this point P onto the XY plane, YZ plane and ZX plane. So that is the whole story about a point which is in the space, in the 3D space. What are the images, what are the projections of this point ABC onto the XY plane, the YZ plane and the ZX plane. So that is the story of a 3D space. Similarly, if you see here in this slide, what is the three-dimensional rectangular coordinate system? Three-dimensional rectangular coordinate system. Basically, rectangular coordinate system is that system in which x, y and z are used, and three-dimensional means x, y and z. If that is two-dimensional, so we will be using x and y. So the Cartesian product, or we may pronounce it this as Cartesian product, because this is three-dimensional. So if we multiply the set of real numbers 3 times, that is the Cartesian product, not a simple product. Cartesian product, r cross r cross r, which can be written as r cube. So this r cube contains ordered triples. This one, this A is from the first R, this B is from the second R, and this C is from the third R. So all ordered triples A comma B comma C such that these A, B, C belongs to each of these R is called three-dimensional rectangular coordinate system. So actually order triple is called the three-dimensional rectangular coordinate system. What is the surface? Surface is made of a three-dimensional analytic geometry, an equation in which x, y, and z are used. An equation in which three variables are used always represent a surface. A surface is always in the 3D space. For example, if you take a football, so you cannot draw a football on a wall. You can plot a square, you can plot a circle on a wall, because these are two-dimensional figures. But if you take a football, or if you take a book, so that book cannot be drawn on a wall, but that book or that football is in the space, in the 3D space. All the surface of that football is made of x, y, and z. So these kinds of figures are called surfaces. Now that is an example that what surface in R cube are represented by the following equations. So we are given R cube, a 3D space, and we are looking for this equation in R cube, that what does R is equal to 3 represents in R cube, and similarly what does y is equal to 5 in R cube. So actually z is equal to 3. If you see this example, z is equal to 3, so it means that z is actually this number c, x, y, z. So z is equal to 3, and x and y may be any numbers, maybe 1, 2, 3, -1, -2, etc., maybe 0. So these two variables x and y can take any value, but this z is actually a specific number, which is 3. So z is 3, and you can vary x and y for along with this z 3. So z is equal to 3 and R cube represent this set, which is a plane parallel to the xy plane. Because z is fixed and x and y can be varied, so there is actually a plane. A plane is made of two variables, order triple, so that's why this is equal to a plane which is parallel to the xy plane. Similarly, if you fix this y, so that will represent a plane and parallel to the zx plane. If you fix this x equal to something else, so that will be a plane parallel to the yz plane. So z is equal to 3 actually represents a plane which is parallel to the xy plane, that plane in which variables can be changed. Z is fixed. Just look at this figure. This is x, this is y, and z is equal to 3. So along z axis take 3 steps up to here, and when z is equal to 3, make a plane which is parallel to this floor. So make a plane which is parallel to the xy plane, the floor, onto z is equal to 3. So this plane is actually z is equal to 3 in 3D space. Similarly, y is equal to 5. So now y is fixed, x and y can be, x and z can be interchanged, can be replaced. So there is actually a plane parallel to the zx plane. So along y-axis, y is equal to 5. We see here, whenever y is equal to 5, so make a plane parallel to the left wall, zx plane over here. Make a wall here at y is equal to 5, which is parallel to this zx plane. So y is equal to 5 is a plane which is parallel to the zx plane. So that's how we we plot planes in which one variable is fixed. In this slide, we are interested actually in the distance formula, that how could we mark distance between 2 points in a space. So for example, let's say P is one point in the space whose coordinates are x1, y1 and z1. Because this is 3D space, so this P will have 3 coordinates x, y, z. Similarly, we are taking the second point Q, whose coordinates are x2, y2 and z2. Now the distance between this P and this Q in the space is represented by PQ absolute, or you may write this PQ without absolute, but absolute is a standard notation. So the distance between P and Q is denoted by PQ absolute, and that is given by this formula. Subtract P from Q. What does it mean? Q minus P along with the square root. So Q minus P, the first coordinate of Q minus the first coordinate of P whole square, plus this plus is in the formula, second coordinate of Q minus second coordinate of P whole square, square is in the formula, plus third coordinate of Q minus the third coordinate of P whole square under the root. So that is the distance between 2 points in the space. Here is an example. Find the distance between P and Q. We see that this P contains 3 coordinates, so that is a 3D point, and this Q also contains 3 coordinates, so that is actually 3D point. So we need to find the distance between P and Q, actually PQ distance. So PQ distance is equal to, we need to subtract P from Q. So the first coordinate of Q minus the first coordinate of P whole square, plus second coordinate of Q minus second coordinate of P whole square, plus third coordinate of Q minus third coordinate of P whole square under the square root. Now calculate these squares, you'll get the distance between P and Q, which is 3 units. So that is how we apply this formula to find the distance between 2 points in the space. Now we have got the definition of coordinate planes and their equations. We have just studied that we have 3 kinds of planes: the floor, which is actually the xy plane, the left wall and the right wall, which are actually yz and zx planes. So these planes are called coordinate planes. And what are their equations? We see here that xy misses z, so the equation of xy plane is z is equal to 0. The equation of yz plane is x is missing, so x is equal to 0, and the equation of zx plane, here y is missing, so y is equal to 0. So z is equal to 0 is the equation of xy plane, x is equal to 0 is the equation of yz plane, and y is equal to 0 is the equation of zx plane. So these are coordinate planes. Now we are having coordinate axes. Axis is the plural of axis. If you write axis with I, axis, so that is singular, and axis along with this e, so that is actually plural. So we have 3 kinds of coordinate axes, namely x-axis, y-axis and z-axis. So these 3 are called coordinate axes. And what are their equations? The equation of x-axis, we see here along x-axis there is no y and there is no z. So y is equal to 0 and z is equal to 0 are the equations of x-axis. Similarly, in y-axis there is no x and z, so x equal to 0 and z is equal to 0 are the equations of y-axis. and similarly x equal to 0 and y is equal to 0 are the equations of z-axis. So along x-axis y is 0, z is 0. We can write a point on x-axis in which x is x and y is 0 and z is 0. This point lies on x-axis. Similarly on y-axis, x is 0, z is 0. So the point on y-axis may be written as x is 0, y is y, and z is 0. Similarly, the point on z-axis is x is 0, y is 0, and z is equal to z. Z is equal to any number. So x is 0, y is 0, and z is equal to z is the point on the z-axis. In this slide, we are going to study the definition of collinear points. So what are collinear points? From the name it is clear that collinear, the points which lie on the same line. If 3 points are lying on the same line, then we say that those points are collinear. So 3 points A, B and C are said to be collinear if they lie on the same line. And how could we know that 3 points lying on the same line? We need to find the distance from A to B, and then the distance from B to C, and then the distance from A to C. So if the distance between AB and the distance between BC, if the sum of these two distances is equal to the third distance AC, then we say that those 3 points are collinear, those 3 points lying on the same line. If this inequality does not hold, then we say that the points do not lie on the same line, they are lying on different lines. So if the distance between the sum of the distances of the sum of those two distances is equal to the third distance, then we say that the points are collinear, otherwise not. So that is actually question number 11 of exercise 12.1. We see that we are asking about the points which lie on the line or not. In the first part we are given 3 points A, B, C, and we see that these 3 points contains 3 coordinates, so these are 3D points. So first of all we need to find distance AB, and then distance BC, and then distance AC. So first of all we have obtained distance AB distance. We need to subtract B from A, B minus A. So 3 minus 2 whole square plus 7 minus 4 whole square plus minus 2 whole square. Calculating this sum, so that is actually square root of 26. So distance AB is equal to the square root of 26. Now in the same manner calculate BC distance. Now BC distance 1 minus 3 whole square plus 3 minus 7 whole square plus 3 minus into minus 2 whole square. So calculate this sum, we'll get square root of 45. Similarly calculate distance AC. So AC distance 1 minus 2 whole square, 3 minus 4 whole square, 3 minus 2 whole square, that is actually the square root of 3. So we see that in these 3 distances we cannot find 2 distances on which adding gives the third distance. So as the sum of 2 distances is not equal to the third distance, that is AB plus BC, if you add AB and BC you cannot get square root of 3. So this is not equal to AC. So we can say from here that these 3 points A, B, C do not lie on a line. If this equality holds, then we say that these 3 points lie on a line. But in this case, the sum of these two distances is not equal to the third distance, so that's why these points are not on the same line. Question number 12 of the same exercise, 12.1. The question is, find the distance of this point 4 minus 2 6 from each of the following. I have taken part A and part D, so we may calculate the distance of this point from xy plane. Recently we have studied that what is the equation of xy plane, or what is the type of a point on xy plane. On xy plane z is equal to 0, so let's say this point is denoted by P. We named this point as P, so this implies x is equal to 4, y is equal to minus 2, and z is equal to 6. So that is from this point. Now on xy plane, z is missing, so z is equal to 0. So P becomes, this point P becomes, z will be taken as 0, x is x and y is y. But x is equal to 4 and y is equal to minus 2. So this is the point on the xy plane, and that point is named as, this point is named as A. So we are going to calculate the distance between this A, which is actually on xy plane, and this point P. So AP distance, subtracting P from A, P minus A, so 4 minus 4 whole square, minus 2 minus 2 whole square, 6 minus 0 whole square, calculating this sum and this square root to get 6. So AP distance is equal to 6. This is the answer of this question, and we see that z is equal to 6, which is actually the z coordinate, that is the same as the value of z. Anyways, this is the distance between A and P, actually the distance between this point P and xy plane. Similarly, in this slide we are going to calculate the distance of that point P from x-axis. Now on x-axis y and z are 0, so point P becomes, x remains the same 4, but y and z are 0. So B 4 comma 0 comma 0 is a point which is on the x-axis. So we name this point as B. Now we need to calculate the distance between this B and this P, BP distance. So BP distance, by using the distance formula, that is the square root of 40. So that is the distance between point P and the x-axis. Now this example is a bit important for you people, that we have just studied that sphere is actually a 3D surface. Sphere means a football. A football is a sphere. A circle is a 2D shape which contains x and y variables. But if we are talking about a sphere, so a sphere is a football, and a football cannot be drawn on a wall, but a football can be considered in a 3D space. So football is actually a sphere. So how could we find the equation of a sphere, the equation of a football whose radius is r and the center is HKL? Just look at this this figure. That is actually a football that is in the space in your room, not on any plane but in the space. So the center of this football will be in the space, and any point which lies in the space containing three variables x, y, and z. X is considered here as h, and y is considered here as k, and z is considered here as l. So that is the center of this football, and definitely it has got the radius, which is denoted by r. So that is the radius. Now let's say on the surface of this football we have taken a point p, x, y, z. You can take this point p here or there, somewhere there. The radius will remain the same because the center is the center of the football. So this point p can be considered anywhere on the surface of a football. So this point p be any point on the sphere. Now by distance formula, this cp distance is actually r, is actually radius. Now cp distance, how could you calculate cp distance? P minus c, x minus h whole square, y minus k whole square, z minus l whole square. That is cp distance is equal to r. Now squaring both sides, if you take square of this side, so this square root will be vanished, and on that side we will get r square. So that is actually the equation of this sphere. This equation represents this sphere whose center is h, k, and l, and whose radius is r. So this is the equation of sphere with center as h, k, and l, and whose radius is r. So whenever you are given the center h, k, l, and you are given the radius r, just replace h, k, l, and r here to get the equation of a sphere. Replace h by its own value, replace k by its own value, replace l by its own value, and replace r by its own value to get the equation of a sphere. This is the standard equation of sphere. Now in this slide we are going to find the equation of a sphere. Find the equation of a sphere with center minus 3, 2, 5, and whose radius is 4. That is the first part of this example. Now concentrate on this part. So given that the center which is actually HKL, which have recently been studied in the previous slide. So this center HKL is given to you people as minus 3 to 5. Now comparing, h is equal to minus 3, k is equal to 2, and l is equal to 5. So these are the values of h, k, and l. And secondly, we are given the radius r is equal to 4. So r is equal to 4, that is given to us. So this is the equation of a sphere. The equation of a sphere, replacing h by its own value, k by its own value, l by its own value, and r by its own value. So whenever we replace h, k, l, and r, we obtained the equation of sphere. This is the equation of this sphere. Now the second part of this question is, what is the intersection of this sphere with YZ plane? What is the intersection of this sphere with YZ plane? We know that along YZ plane there is no x, so x is equal to 0. So whenever this is the equation of the sphere, if we replace x is equal to 0 in this sphere, we will be able to find the intersection of this sphere with YZ plane. So for intersection with YZ plane, along YZ plane x is equal to 0, so put x is equal to 0 in this equation. Whenever you put x is equal to 0 in this equation, so that is equal to 0, that is 3. 0 plus 3 whole square is 9. Now shifting this 9 towards that side to get 16 minus 9, which is equal to 7. So that is actually is y minus z whole square. Z minus 5 whole square is equal to, this 7 can be written as square root of 7 whole square. So this equation is looking like just like the equation of sphere, but it contains only two variables. So it means that is the reflection of that sphere on the YZ plane. The reflection of the sphere on the YZ plane is looking just like a circle. So that is actually a circle. A circle contains two variables. That is a 2D shape. So that is the equation of a circle on the YZ plane, whose center is 2 and 5. 2 and 5, x is actually equal to 0. So x is 0, y is 2, and z is 5 is the center, and the radius is actually the square root of 7. So this is how we find the equation of a sphere and the intersection of the sphere on any plane. If that is xz plane, so we will put y is equal to 0 in the equation. If that is xy plane, so we will put z is equal to 0 in the equation to get the intersections. Question number 17 through 22 of exercise 12.1. It asks us to show that the equations represent a sphere and find the center and radius. 17 through 22. This kind of equation will be given to you in these questions. We are going to show that this kind of equation represent a sphere. We know the equation of a sphere is x minus h whole square, y minus k whole square, and z minus l whole square is equal to r square is the equation of a sphere. So first of all, we need to convert this equation by completion of square method to that standard equation, and then comparison will give us the center and radius of that sphere. So first of all, this is a given equation combining the terms containing x, this term and that term, combining the terms containing y, and combining the terms containing z is equal to 15. Now this step is very much important, which is coming here. That is x square minus 2x. The coefficient of x is 2. The coefficient of y is 4. The coefficient of z is 8. We need to add the square of half of the coefficients of x, y, and z on both sides. So that is that we are going to add the square of half of the coefficients of x, y, and z on both sides. What does it mean? This is the coefficient of x. Half of 2 is 1. So adding 1 square here and there. Half of 4 is 2. So adding 2 square here and there. Half of 8 is 4. So adding square of 4 here and there. So that's how we write this step, that we are going to add 1 square here and there on that side, 2 square here and there, and 4 square here and there. Now from here, x square minus 2x plus 1 whole square is actually x minus 1 whole square, and this is y square minus 4y plus 2 square is y minus 2 whole square, and this is actually z plus 4 whole square because this is plus, and that side is 15 plus 1 plus 4 plus 16 is 36. So that is x minus 1 whole square, y minus 2 whole square, and this plus can be written as z minus into minus 4 whole square, and 36 can be written as 6 square. Now this is looking like the standard equation of a sphere. Comparing this equation with the standard equation of a sphere, and from here we will get h is equal to 1, k is equal to 2, l is equal to minus 4, r is equal to 6. So those are the values. So therefore center, which is actually hkl, h is 1, k is 2, l is minus 4, and radius is 6. So this equation represents a sphere with center 1 2 minus 4 and radius 6. So that is how we show that this equation represents a sphere, that we have combined the x terms, y terms and z terms, and then this statement is very important, that we are going to add the square of half of the coefficients of x, y and z to get the equation of a sphere.